Oh, yeah. Sure. Thank you very much. Mm. So, yeah. Uh, as in, to start with, as we can actually say that, this paper, this is one of such paper which actually doesn't need much of an introduction. Because this is one of the revolutionary paper which has changed the way NLP was actually thinking before, and NLP was after the paper. So with such a revolutionary paper like attention is all you need, or the transformers architecture, let's actually see first what was the era before the transformers. Obviously, post the deep learning, what is the era before the transformers? How effective was the transformers? Have actually changed the entire way of working. To start with, around 2013 was a golden era for image related problem statements. So let that be classifications to a certain extent, might not be in the later stages object detection and all, but the foundations of classifications, object detections, all these things were actually been doing good with something called as convolutional neural networks. And also these networks were winning awards, winning competitions, something like as an ImageNet competition and all. And post this era, but at the same time, though it was not such a good period for NLP related things, but there were a baby steps towards this direction in the NLP field, wherein we had around in the same period of 2013 something called as word to vec, wherein the introduction of words to be converted into embeddings have actually happened. And then direction towards the embeddings, direction towards getting into the embedding directions. And post that, around in 2014-15, was the period for recurrent neural networks, wherein you would actually not only have your words or sentences to be converted into embeddings, but also solve problems like classification, like sequence to sequence, applications, something like a mission translation, summarization, etc. Wherein again, RNNs used to be one of the revolutionary architecture where you could able to solve many of the problems with RNNs, many of these such kind of an applications with RNNs in the field of specially NLP. Now, post this, 2014-15, uh, in 15-16, we had something called as an one of a very important concept called as an attention, wherein people have started getting into the idea of you need not actually look into your entire text for you to give you the classified answer. Just look at some of the words, or what are the words which are actually impacting the decision of getting into that getting into that class, or getting into that mission translation. What are those important words that are actually affecting the entire decision of the model? So there comes the concept of attention around in 2015-16. But because the revolutionary the RNNs were actually working good at that period of time, this attention was usually used on top of the RNNs or LSTMs or GRUs for it to get the answers. Now, what is the major drawback of RNNs or LSTMs? Is the only aspect is it actually does a sequential processing. Now, what it means, it actually considers one single word at a time. And for a fourth word or a fifth word to process, it has to process all the first three or four words. Only then it can actually reach towards fifth word. Now, because this has been the scenario, it is very difficult for for training this RNNs or LSTMs on a very big big data sets, and it's very difficult to handle to effectively reuse the algorithms and use it for big data sets. That has been relatively challenging. Now, when that was the issue, where sequential processing was the issue, the alternative that they actually found for all, RNNs at that point of times were again CNNs. CNNs were relatively parallel. So what they've actually started working on is that, they picked up the CNNs and then use it for the NLP problems like sequence to sequence. Like S2S is nothing but using convolutional networks for sequence to sequence architecture. So ByteNet is nothing but using convolutionals on top of your encoder decoder architectures. So because convolutions are usually parallel in nature, these were the experiments that have been done to avoid the sequential processing. But the problem was, first, they were not that effective. And the second is the long range dependencies or the dependencies within the within the document were not being captured properly. So the long range dependency here, I mean, if I'm actually having a context in a first part of the document and also in the last part of the document, now these dependencies are not being captured using the conf S2S or ByteNet or any of these convolutional based architectures. Now, Bancon in 2017, with this in actually mind, transformers have actually evolved, wherein it has completely removed the sequential processing, concept. It has actually completely taken out the recurrent neural networks out of the picture, and then we're using only attention based mechanism on top of your encoders and decoders. That would actually revolutionize the entire processing. And post that, there were many things that this transformers could able to achieve on top of the sequential processing. Now let's actually see what are all these things that transformers could able to achieve on top of the like you know and on top of the other previous architectures. First, as we have just discussed, the parallel processing, which has been very important aspect, because transformers didn't had that dependency that to process the fifth word, I have to actually see the four words. That dependency wasn't there for transformers. It is actually very easy to process it parallelly, and so could able to utilize its GPU, and so it can actually scale it to a large extent that you can actually give trillions of tokens today, even to the simple models. We can actually give trillions of tokens because of the basic scalability and GPU utilization that transformers could able to do. Then the third, transfer learning. Though I should say, to a certain extent, the previous architectures were actually having the transfer learning, but transformers were relatively very effective in doing the transfer learning, because they could able to generalize very effectively compared to the previous models. So transfer learning being also one of the I should say important distinguishing feature from the previous network. Interpretability or the explainability. Now it comes to previous what I should say architectures, whether there be RNNs or LSTMs, if attention is not present, it was very hard to interpret why did we actually get that particular answer. Why did the data has been classified into a particular class. I mean, we never actually could able to interpret it properly. On the other hand, because of attention, transformers could able to interpret the result as well properly. And then, I mean, now even we actually have the sources of information where where it is actually being captured. So the interpretability is relatively another distinguishing feature. Long range dependencies. Now, because transformers would actually consider the entire text while learning, the long range dependency of having a context in the first part of the document to this last part of the document, that particular dependencies are all being captured in the transformers. Language agnostic, though the language agnostic feature was even present in the previous architectures, as I mentioned earlier in transfer learning as well. This was doing relatively effectively. Language agnostic is nothing but you can actually input any language to the transformer. And also multimodal, again the same thing. Like, a multimodal is also something that transformers is actually been effectively doing, that you can actually give, you can actually train your transformer with the text or image or video or all of them together, and then can actually, and then transformer could able to give an amazing results. So compared to the previous architectures, these being the very distinguished, what I should say, features of transformers compared to what it had earlier. Let's actually look into the architecture which has made this transformers to be very distinguished compared to the previous things. Now, this being the architecture entirely, they are input embeddings, positional embeddings, encoders, decoders, multi-head attentions, feed-forward networks, add and norm, softmax. Now we'll get into each of the things in detail in the coming slides, and then see where is the parallel processing has happening, where is the like I mean the entire architecture we'd actually look into a little more in detail. Now coming to the first part, the input embeddings and the positional embeddings. The water embeddings are nothing but obviously you would convert your text into the semantic representation using the words, using the numbers. So you'll convert your text into set of numbers which would represent the semantically your text. Now, when you are actually having a set of numbers, they were two embeddings which this particular architecture, the transformer architecture would actually have. One being the input embeddings, the other being the positional embeddings. Now, input embeddings is nothing but the text whatever you are actually having, the embeddings of those text is nothing but the input embeddings. So if I'm actually having how are you as a sentence, the embeddings of that how are you is the input embeddings. And this is a normal embedding layer, learned embedding layer, which will train throughout the what I should say, throughout the architecture. There is a second and one of the important concepts, especially in the transformers, is nothing but the positional embeddings. I'll just get into a little more detail on positional embeddings. But over here, if you can actually see, what we will do is we will actually add upon the input embeddings and positional embeddings, add them both, and then give it as an input either to the encoder or to the decoder. That is what we'd actually do. Now we'll actually get into in depth as in what is positional embeddings and why do we need that. Now positional embeddings is nothing but, now if because transformer architecture, as we have discussed, it actually does a parallel processing. So it will consider all the words at a time and then it actually does the parallel processing. Now if it is actually doing all the words at a time, now if I'm having how are you or are how you or jumbled upon words, it doesn't matter, frankly, if you don't have something called as an positional encoding on top of it. If you actually need to say that I just want how are you, as how in the 0th person are in the first person and you in the third person, you need to give that positional information explicitly on top of your input embedding such that it can able to understand the position of each and every word. Now, given this the scenario, we can simply give saying that, how is it a 0 position, are you are at a 1 position and you at a 2 position and so on and so forth, till XYZ at a 1 lakh or 1 million or whatever be the position it is. But what is the intuition? I mean, why do we actually need these positional embeddings? Is that if I'm actually having my input embeddings at a particular position in my graph, and I want to actually what I'm willing to do is to shift this input embeddings to a certain extent towards the direction of the position. So the same word which is in a position 0 would actually have a different embedding, and the same word which is at a position 5 would actually have a different embeddings because of this little shift in the positional aspect that we are adding upon. Now, if we actually do this little shift, I mean, if this is our main aim to do that, I just want a little shift from my input embeddings. Now, in the previous case that we have seen, like if I'm having 1 million or one, whatever be the number, then the input embeddings would go drastically haywire here and there. And that is the reason why we would actually not go with any of the conventional methods of decoding the positional embeddings. Rather, what is actually being preferred is to give an embedding for each and every word within a sentence. Now I'm actually giving each embedding. That's fine. Like how would I actually give the embedding? What is the basis that I actually give this embeddings? Now for that, what they have actually discovered is that there is alternate sine and cosine values is something that you can use. That first, let's say if I'm actually having a sine curve with a particular frequency, this sine curve would actually help me fill the values for my first position. So over here, this sine curve would actually give me the positions for point 0.3, point 0.1, minus point 0.9, and so on and so forth. Now I'd alternatively use my cosine curve to give the second values, like something like zero point 0.8 minus zero point 0.7 minus zero point 0.8, and so on and so forth. Then again, the third sine curve with a different frequency would give me my zero point 0.2, zero point 0.9, zero point 0.9, so on. And then the cosine curve, and so on and so forth. This is the approach that they have actually come up. We'll also see a little why is this approach, but then this is the approach that they have actually come up to get this embeddings for each and every word, like sine, cosine, alternate values with different frequencies. Now why is only sine and cosine functions is actually being used? The reason behind is that sine and cosine would actually always maintain the relative distance between two words. So what I meant over here is, if I'm actually having how and you at a two distant position, then that relative distance is always being maintained using the sine and cosine values. That is the reason why they have actually picked up sine and cosine functions for them to hmm, in fill up the embedding space. On top of it, this is irrespective of the sequence length that we are actually dealing about, or the words, the words can be anything, still the position embeddings will be the same. So that is also something which is important. And whatever be the sequence length, I have 1 million or 2 million, whatever be the number, I still have an embeddings which is of a little distance from my input embeddings, not not a very distance. It cannot be so large. That is the reason why they have actually chooses positional embeddings. So as we have just seen, so now the input embeddings with the positional embedding summation would actually be the input for encoder and decoder. This being all about embeddings, my input and positional embeddings. So I just want to say here, interrupt me whenever I'm not clear, or do you have any queries, please interrupt me. I'd be more than happy to answer any of the questions. So, this being I should say, the input and the positional embeddings, now let's actually see the encoder. Now let's see the next level of architecture, which is the encoder and the decoder. Now,
Mahati, I think we have a question.
okay,
Neeraj?
sure.
Yeah, Mehdi, thank you for presenting this paper.
Thank you.
Um, I always find difficult to understand this. So you just mentioned that because of the distance of why we are not taking the positional encoding as 1, 2, 3, 4, and all, because of the distance. Can you please repeat? Yes, this part
Uh-huh.
one more time.
Okay. So what I meant over here is, I actually have my input embeddings, and I also have the aim of having a positional embeddings is to orient my input embeddings to a little distance. such that it would learn along with the input, it will learn the position of that data as well, because it is important to learn the position as well for a sentence, because the flow of the data is actually important. But then, if we actually use the numbers like 1, 2, 3, 4, that is still fine because we are only seeing 1, 2, 3, 4. But if it is 1 million, or because within a particular document, you can even have very big number of words. So if there is a 1 million or a 1 lakh set of documents, then the input was positional embeddings, whatever the orientation from the input data, it will be very far.
Oh.
So it is the essence of the input embeddings is lost in this scenario. So we want the essence of the input embeddings also present, and also we want the flavor of positional embeddings to be added on top of it.
You are trying to say that when the first word, suppose how is on the 0th position, and say you is on some 1,000 or 1 lakh position. So in that case, this distance, because of the position we are taking 0 in comparison to 1 lakh, will be too much, and that will create this variation on the distance. It will create the huge.
Yes, absolutely. So 1 lakh, if I'm adding 1 lakh to my the scale that it would actually go, I mean, the input embeddings, the essence is lost there.
Yes, yes.
The input embeddings is of no use in this scenario.
Yeah, got it. Thank you. Thank you for repeating.
I think Ashank also has a question.
Yeah, hi Maheti. First of all, thank you again for presenting this paper. I think it's very interesting so far. So my question is, what I understood of the positional embeddings, it is very similar to something like a normalization that you do of input variables before you begin any modeling process. So my question is that, is positional embeddings a feature that originated after the attention networks, or even before that the CNNs and the RNNs and the LSTMs, they also had positional embeddings?
So over here, I just want to little say about the normalization, the difference between normalization and positional embeddings.
Sure.
So the positional embeddings over here, right? Normalization we actually use such that we want to converge very fast. So we make sure that it is in a distribution. Okay, but then in positional embeddings, what we're more focusing on is that we want the relative distances to be captured. So the absolute position and the relative distances. So in this scenario, what I meant over here is if I have to actually say again, there is an one input embedding which has been let's say this is for how. Okay, how is this input embedding which has been moved to a certain extent for the second embedding, input but positional. Now there is one more embedding for R, which is again around this place, let's say, will be around moved near to my I mean this position, let's say. I mean you could able to see my mouse, right?
Yes.
Yeah. So if there is an R over here, it is near to my how again. So which means this relativeness is something that I want to maintain throughout my throughout my data. This is the main objective of positional embeddings, rather than it being between 0 and 1. I mean 0 and 1 is true, but the main main focus is to maintain that relativity and to maintain that absolute distances, positions. Okay, so I'm sorry, I actually forgot your question.
Was this positional embeddings a part even before the attention networks, like in LSTMs or before?
And I mean, what they've actually mentioned in the paper is no, they have actually introduced in the transformers the positional embeddings, because this was the only start where that they have actually removed that part of what I should say sequential processing. So that being the major thing, now you can actually process the entire data at once. So when you're actually doing entire data at once, uh, uh, I mean, you need at some point of time the positional information. So what they have actually mentioned is they have introduced it.
Got it. Thank you. Thank you. That's very clear. Thank you.
Thank you. Yeah. So, getting back to that, post this input and positional embeddings. Now, getting back to this encoder and the decoder, architectures. Now, I mean, what is the main aim of, or what is the main problem statement of the paper is to solve a sequence to sequence task. Now, what is the sequence to sequence task that they have actually picked up is a mission translation. So, what they're doing in the paper is that you would actually give your source language, how are you, let's say, and then you would actually get your output, aap kaise ho. Now, frankly, in the paper, it is not Hindi. I just actually want to make it a little more Indianized, so I've actually made it Hindi. But in the paper, it was French and German. So, if I'm actually having my input sentence, how are you? The output, expected output is aap kaise ho. Now, if they're solving this particular problem, in this scenario, the role of an encoder is more like you have to summarize your data and encapsulate it into embeddings. So, what it does is that it would take the source language, English in this scenario, it would encapsulate it would summarize the essence of this, source language into a set of embeddings. That embeddings would actually have the semantic meaning again of your source language. So the main aim of the encoder is to encapsulate the data into a set of embeddings. Now, what is the aim of a decoder? Decoder has to actually get this, encapsulated data, understand that semantics, and then generate the text in the source language. So when you're generating, so the main aim of the decoder is to generate the text in the in the source target language. So in short, the aim of encoder is to summarize, and the aim of the decoder is to generate the data. Now, on top of it, there is a concept called as auto-regressive, which is nothing but it will consume its own previous output as well, and then produce the present output. So that is also I mean, throughout the architecture, what Transformers does. So it is actually called as an auto-regressive platform. So encoder and decoder, summarization, and the generation being the major things. Now, if we actually get into a little more in
Okay,
depth.
just a sec. Ashank, you still have another question?
Oh no, sorry, my hand wasn't raised.
Not a problem.
Sorry.
And folks, I think speaker is generally not able to see hands raised. So
Yeah,
I suggest please unmute yourself and go ahead.
sure. Yeah, that would be of great help. Thanks, Anuj. Yeah. So if I can, if I get into what is the encoder, let's actually get into a little more in depth of it. So encoder is nothing but one, a six identical layers stacked upon each other. In this particular paper, it is six identical layers. It might be different for a different architecture again. So six identical layers stacked upon one another. Now, each encoder would actually have four things: the multi-head attention, feed-forward neural network, residual layer, and the layer normalization. We'll go in depth of each and every layer in detail in the coming slides. But these being four important sublayers of an encoder, I should say. Now, dimension throughout the architecture is 512. Again, I'll actually mention you why is the dimension is 512 in the latest slides. And again, now coming to the decoder, decoder is again a six identical layers stacked upon each other. And of each layer, as you can see, there is this particular part is actually similar to what the encoder is: multi-head attention, add and norm, feed forward, residual layer and the normalization layer. There is one more part of it which is mask multi-head attention, which is nothing but, if you can actually see, the input is usually masked. So what I meant is, when I'm actually seeing aap kaise ho, in encoder, you would actually give the entire input, like how are you, as in at once. But in decoder, because it has to generate the next output, you will give one token at a time. That has actually been something we would actually say as a um, mask multi-head attention, that the input is actually masked and actually given one at a time. Now, if we actually get into the details of very much in detail of the sub layers, the first one that we actually picked up is the multi-head attention. Now, I just want to say an analogy for the multi-head attention, such that it is relatively easy for to grasp. Now, let's say I have a teacher in a classroom of classroom full of kids. Now, the teacher wants to pick a set of students who are, who are capable of doing a particular task. So, teacher want to pick a set of students who are capable of doing a particular task. That is the main aim of the teacher. Now, what the teacher asks the students to do is three things. The first thing is the teacher asks the students to raise their hands to, and then whomever they feel are capable of doing this particular task. So the teacher asks the students to raise their hands who are capable of doing this task. The second thing the teacher have actually asked is to keep a special spectacles. Now, these spectacles would actually reflect what the importance of other students in the class. So the color of the specs would change according to the importance of other students in the class. So the teacher have actually asked the second thing to do is to keep a spectacles. The third thing that the teacher actually asked to do is to jot down the importance of what I should say about they themselves. You write it about your biodata, let's say your name and what are you good at and all the aspects of you yourself, and then hold it. This is a third thing that the teacher have actually asked to do. And now what teacher is doing is, based on these three things, teacher would actually give the, teacher would actually pick up the important students. Now, in this analogy, in this scenario of attention, can you a little guess what can be the, analogy that we are looking out for? What is teacher? Who is teacher in this scenario? Or who is the students? Any guesses? So in this analogy, the one that we are looking out for is the teacher is the model. So what the model is actually trying to do is to pick up some words or tokens which are important to do a particular task, which is mission translation in this scenario. So attentively pick up those set of tasks which are actually important to do a particular task. So the students in this scenario are the words or tokens, and the model is nothing but, and the teacher is nothing but the model. Now, what are these three things? What we call as a query, key, and value pairs. So there are three different aspects of a particular word that we are looking out for. And based on these three things, we are actually saying, we are giving a attention score to each and every word or token. And then this entire mechanism, which would actually do using query, key, value pairs, we are actually giving an attention for a particular word, is nothing but the attention mechanism. So the teacher is actually adopting an attention mechanism here to pick up the important students. Now, there can be a scenario again, obviously, teacher can actually initially don't have any idea about any of the students when she was just introduced to the class. So do the weights of our model. Sorry about that. And during the training, the teacher would actually ask the teacher know about each and every student, and then pick up more what I should say knowledgeably. The same thing would actually the model would also do, that the model would pick up the words based on the training, which one is actually better than the other. And also the other part which I want to say is, some of the teachers might be interested into students who are good at the value, and some of the students, teachers might be interested into students who are good at query in this aspect. Similarly is the model, like can be different attention mechanisms which would weigh differently for all these three pairs: query, key, and value pairs. I guess I hope I'm actually clear. Then we'll get into the math of the paper. So in this in this input, as we just discussed, the words or tokens is nothing but the students. Now, keeping that as just an analogy, let's actually get into this. Like, you actually have a set of words or tokens, and you obviously have three parameters associated: query, key, and value vectors. Now, how are we getting this query, key, and value vectors? Is based on my input embeddings. Now, I have an input embeddings, as we have seen, previously in the previous slides. I have an input embeddings. Now, the input embeddings here is the both addition of input and the positional embeddings. So I actually have that input and positional embeddings here, and then I actually pass it through a linear projection, which also something I'll show it in the future slides. We'll actually send it through a linear projection to get queries, key, and value pairs. Now, these three things, as I mentioned, is three different aspects of your input embedding. Now, if I'm actually having this query, key, and value pair, what I'm actually doing is the manipulations on top of these values is nothing but, first I actually do a query and key dot product, and then I'd actually have a particular score, which is nothing but my attention score. And this attention score is ultimately multiplied with my value vector. Now, before me multiplying with the value vector, this score is ultimately being multiplied with the value vector. But before me multiplying, I'm doing two steps to scale down my values, because again, because these are very big values. If I keep multiplying this with my value vectors, the values will also be very very big. That is the reason behind I'll scaling down, dividing it by under root of dimension, and then applying a softmax. The main aim of applying a softmax is nothing but all the values will be between 0 and 1. So that is the reason I would actually apply a softmax on top of it. And now I'd actually multiply my softmax with a value vector, which would give me a set of values. These values, aggregation of these values is nothing but my, what I should say, z vector. Z vector is nothing but the aggregation of all the value vectors. And this Z1 is associated with the word, the input word thinking. So in this scenario, if you see this thinking is one particular vector, we would actually do manipulations on top of all the data. And then we'd actually have a Z, Z vector for this particular input. So I do this as dot products, I'll scale down, I'll multiply with the value vectors, I'll do it with all the data, and then I'll get this Z score. This is nothing but the scale dot product attention, which is being mentioned in the paper with the given formula. That is that your query key transpose is multiplied, divided by your dimension, applied a softmax on top of it, and then multiply with your value vector. This is the attention score or the scale dot product attention, which has been mentioned in the paper. I hope I'm actually clear till this point.
Yeah. So Mehdi, every word is having a Z score.
Yes, yes. Every word would actually have the Z
And
score.
that Z score is relative to all the words.
Yes,
So,
absolutely. So that Z score, I mean, every word based on its input, embeddings would actually be divided into three key query value. And this key query value of all the words, I mean, the vector representation would actually be, the coming slides would actually have, but still these values of all the words is something that you manipulate here. See, query with key of this particular word, thinking with thinking, and thinking with missions.
yes. So simply talking, it's like n square operations because every word
Absolutely.
has to do, and as the number of words will keep increasing, the speed or the time taken to process this whole thing will keep increasing.
Absolutely. Absolutely.
Mhm.
And that this is the base. I mean, I should say the scale dot product attention is the base of the entire parallel processing idea as well. So here, if you see, you're not now considering any position. You give the entire
Correct.
data and you do the entire manipulations. So there's no sequence in this scenario anymore. So because of that, they are n square operations, as you have mentioned, absolutely correct. But then, because of the GPU capabilities, uh, we can actually do it relatively faster.
Yeah, I think that's why we need more GPU capabilities for the
Yes, yes,
transformer models.
absolutely, absolutely.
So, Mahati, just a quick question. So, like you usually train it by sending various tokens at a time, which might be like 10 words at a time. So, if you have a very large, let's say, corpus of
Mhm.
words, the long range dependencies are like they're in a different part of the model, right? Or is it in this part?
And they're the same part. The long range dependencies are in the same part. So now if you can actually see, right, if there is a sentence, like let's say scale dot protect attention, if that is a particular sentence, now I would actually use my entire, let's say there are four words. So I have 4 by 4 matrix manipulations. Now let's say dot product is more oriented towards attention than scaled. I mean, mm, over here it is nothing the case, but
Mhm.
then if I'm actually having some kind of an orientation, that orientation is also reflected in this set of embeddings only.
Right, but let's say the scale dot product attention is just 4 words from a very large paper that has thousands of words.
Ah.
So the long range dependency between the words at the beginning of the paper and at the end of the paper, where will that get captured?
So as we are actually right now, I mean, as the paper suggests, though, I mean, it is not the case, frankly, for higher end of models. But as the paper suggests, if we are having n words in a particular document, you would actually do the n words at a time. So if we are actually doing n words at a time, the long range dependencies is also been captured in a similar way. So what I meant over here is when it is actually training, let's say there is a reference of let's say Modi in the starting of a particular article, and also the prime minister, let's say, being referred at the end of the article. This
Mhm.
is what you're talking about, no? Long
Right,
range. Yes.
right.
So when I'm actually giving this entire thing, the prime minister, when it is when the attention scores of all the prime minister is actually being taken, the reference of prime minister to the Narendra Modi is captured in this scenario only. When you actually calculate, if you see the value vectors, now the V1 is relatively darker and V2 is relatively lighter. That is nothing but the attention that it is actually giving. So
Okay.
that attention is actually being captured in this scenario only.
Got it. Got it. Okay. Thank you.
Yeah.
Mahati, what is T in the equation? QK bar
Key
T.
transpose, it's we're making a transpose for the matrix.
Got it. And
That's, sorry.
square root of dk. What does that mean?
Okay, that is the dimension. The dimension part I'll actually little get into in the later slides, but that is a dimension. But this dimension is nothing but the dimension of my query key values. So 64 being the dimension of the query key values. Now underscore of dk would be my 8 value in this scenario.
So when you say dimension, is it the number of
Uh-huh.
tokens?
Yes, number of elements in a vector.
Got it. So that's the input vector, is it?
No, not the input vector. The query key and value vectors.
Got it. So
Yeah.
in terms of machine, I mean, thinking from machine's perspective, Can you talk about QKV one more time, please?
Uh, so I didn't actually get that question. I'm sorry.
Um,
Mission's perspective is
like when the machine gets a prompt, what is QKV uh, in that process, in the whole process? What is Q? What is K? What is V?
okay, fine. So what if I understood it correctly, frankly, the thing is like I'm having an input, like thinking machines, let's say, right? So now, how my thinking machines are being converted into QKV was your question, if I get it correct.
Yeah, yeah.
Yeah. Okay. So first, the thinking machines will be converted into input embeddings, the embeddings that we have actually just seen. And yeah, as like the next slide is all about that. This particular input embeddings will be sent through a linear projection. So whenever we actually say a linear projection in the context of machine learning, it is that thing, but we multiply with a weight matrix.
Right.
This is learnable weight matrix. So throughout the what I should say, throughout the architecture, these weights are learned. So this input matrix, let's say X is the input matrix in this scenario, is multiplied with a set of learnable weight matrices, which would actually give me my query, key, and value vectors.
Okay, so there
Linear.
are three different weight vectors multiplied with the original prompt, is it?
Yes, absolutely.
Correct.
Mhm.
And if you can go back to the old slide, previous slide. So here you mentioned the value would be calculated by multiplying softmax with the score.
Hmm.
Uh, if that's the case, then how come in the next slide we are evaluating vector by multiplying a vector weight with x?
So one second. So the thing over here is, so what I'm showing in the next slide, now this particular slide, is
Mhm.
about the first few things. Like, your embedding is converted to query key values. This particular, I mean, these three, the Q1, K1, V1, how are they being generated is shown in this particular slide.
Got it.
This
So
V is nothing but this Q1, K1, V1. Now, after I get Q1, K1, V1, I do Q1 and dot K1,
mhm.
and then do a certain manipulations on top of data, which is nothing but the representation of this particular score.
Right, that's basically normalizing the value between 0 to 1.
Yes, absolutely. This is nothing but normalizing the value. And after normalizing, then I'll actually multiply with my V1.
Got it. Got it. Understood. Thank you.
This is the attention score we are saying about, because if you can see, the values of V1 fade out or like, increase because of these scores. Like, this attention scores would actually differ the importance of the my V1 value vectors. That's again to the answer of long range dependencies. Again, these scores would also give me that essence of how important another word to this particular word. So Prime Minister to Narendra Modi, how important is this? Is this attention score would decide.
Got it. So the whole flow, it will, for every prompt, there will be a set of queries executed, and on top of that, it'll return a set of keys, and using those set of keys, the machine evaluates where the position of a particular token should be assigned. Is that a right way to summarize?
To a certain extent, yes, but we are not actually summarizing the position of a particular word over here. We are actually summarizing how important is the other word to this particular word. That is what we are actually seeing in this scenario. So when you are actually talking about positional embeddings, that is where we are actually dealing with how important is that particular word. Okay.
Right.
In this scenario, after the entire calculations, what we are actually setting up over here is how important are each words to another words. That is one thing that first we are calculating. And based on all these important levels, we would actually get an aggregate, aggregate sum.
Got it. And comparing this with conservative models like RNNC. And so there, in conservative NLP models, there the execution used to happen word by word. So
Yes.
here, when we when the machine is processing all this, so uh, here the weightage would be assigned to the word next to it or across the sentence.
No, no, no. So the weightage is actually assigned based on what is important.
So that's the attention thing.
That is the attention thing, which they'll learn through the process. So when they're predicting the next word, throughout the entire flow, they'll actually learn the entire which words are actually important to another set of words.
Got it. One last question.
Yeah.
So in the equation,
Mm-hmm.
apart from the factorial, what does softmax mean here? Is it a different function, different formula for that?
So softmax, as I just mentioned, it is nothing but to normalize the values
Got it. Okay,
between 0 and 1. That's it.
understood. Thank you. Thanks a lot for answering all the questions.
Thank you. I was just worrying about the time. That's it.
Understood.
Yeah.
I'm really sorry for
No,
eating
no,
up.
no, 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 completely fine. Yeah. So as we have just seen, this input embeddings would actually send through a linear projection. Linear projection again is nothing but a set of weight vectors. Now, yes, first thing is we have converted that one particular vector into a matrix. So here my thinking mission is into a matrix. So even in the case of the entire document is converted into a matrix of all the vectors. And now these set of vectors is manipulated, matrix manipulations with the set of weight vectors to give us the ultimate result. So in this scenario, it is a linear projection where we actually get query, key, and value vectors. And again, this is nothing but a matrix representation of the formula that we have just seen, that query into K transpose would divided by dimension with the softmax multiplied with the value vector would give me my Z vector or Z matrix in this scenario. Sorry, Z matrix. Now this is if it actually this is nothing but a self attention wherein I actually process this entire on a single sentence, let's say. Now, let's say we are actually looking out for in the architecture. It is not a single head or a self attention. They are not synonymous, but then yes, for now, in a single head attention. But right now, when you're actually looking out for a in the architecture, it is more of a multi-head attention. Now, what is a multi-head attention? Again, we'll actually see with an analogy. Now, let's say I want to read a particular book. Now, rather than me reading the book, what I thought of doing is I'll call 4 more people and I'll give the book to these 4 people and then ask them to read. Now, when I'm actually getting the 4 people, I make sure that they are of diverse, diverse feature sets. Like, one person is a female, one person is a male, one is a kid, and one is a elderly person. And then I ask them to I'll give this book to them and then ask them to read. Now, when they are actually reading this particular book, let's say the young kid is more more oriented to read about the fictitious aspects of the book. Let's say the elderly person is more interested to read about the values present in the book, and so on and so forth. Each person would actually have that their own individual interest or their own individual attention in this scenario and to read the book. Now, after they have actually completed reading, now what I'm actually saying them to do is come close, discuss among yourselves what have you actually read, and then you give me the summary. So when they're coming and discussing among themselves, they're making sure that all the aspects are being covered properly, or the attention which has to be given, the higher attention will be given the higher attention, the remaining will be given the less attention. They make sure that this interactions happens quite properly, and then post that they would actually give the summary to me. So so what actually happens even in the scenario of multi-head attention is also that the same thing, that my input matrix, the X, I'm actually giving it to multiple attention heads, wherein what in this scenario, what they have actually observed is one particular attention head when it is actually giving importance to, let's say, parsing. The other particular attention, let's say, it is giving importance to parts of speech of the sentence, and so on and so forth. Like, multiple attentions would actually have multiple orientations, and then lastly, so they'll actually have each attention head for a particular, for a particular input. Each attention would actually have their own Z matrices. Now, once I actually have a set of Z matrices, now what I'm actually doing is I'm concatenating all these Z matrices, multiplying with a weight matrix. When I'm multiplying with a weight matrix, which is again a learnable weight matrix, now what I'm actually doing is I'm consolidating the result of my multiple Z matrices, and then I'm actually getting an ultimate Z matrix, which actually have the ultimate attention to which word has to be actually given more attention, and which word is more related to another word, and so on and so forth. This information is actually being present in the consolidated Z matrix. So this is my multi-head attention part, which I'm actually having. I hope I'm clear till this point. Now, yeah, sorry. Now, I just want to say where is this particular attention is used in the same architecture. Now, in this architecture, where is this attention been used? Now, in the encoder-decoder architecture, what it actually does is that the keys and values, as we have seen, right, query key values, the keys and values of the source language is given to the decoder from the encoder, and the query will be taken from the output or the target language. So English language keys and values are given to decoder, and Hindi language queries are given to decoder, and the decoder would actually generate the Hindi language. So when you're actually giving these key values or the queries, the attention weights would actually give me the essence again about which words are relatively important and which words are relatively not important in this context of in the given input context is usually being given by the encoder to the decoder, and also from the output you would actually have some similar vectors of queries, and so the decoder could able to generate. This is the usage of attention with an encoder decoder based architecture. Now with an encoder, as we have seen, this is an autoregressive architecture. So the previously generated output, so whatever be the output that has been generated, which would actually say that how is important. Let's say, this is very hypothetical scenario, like wherein in the first place is actually saying that how is very important word, and based on that it would actually generate in the next layer that okay, how is important, and you is also little important, kind of, it will add upon saying that you is also little important. So this kind of learning from the previous outputs is also done using attention in the encoder layer, and similar to that of in the decoder as well. Rather, decoder just generates the output. When it's generating the output, it will actually see what are the attentions of the words which are given in the previous output, and based on that it would actually generate the newer outputs. This is how the encoder, decoder, and encoder decoder architectures, the attention is used in these architectures. Now, till now, what we have actually seen is the input embeddings, the positional embeddings, the encoder, decoder, and the multi-head attention. Now, the other important layer, which is little given little importance, but then one of the important in this scenario is the feed-forward fully connected layer. Now, if we get into a little more details of what is a position-wise feed-forward layer, it is nothing but a fully connected layer present after what multi-head attention is. Usually, in the neural network scenario, when we actually have a fully connected layer, the main aim of the fully connected layer is to understand the complexity of the data. So apart from the which words are important and how is the parsing done and all the things, to understand the complexity or the nuances of the data is also important, which is being captured in the feed forward fully connected fully connected layer, which is nothing but what we say as a two linear transformations and one ReLU activation. As as you can see, if I'm actually having a vector with x1, x2, x3 as my input values, thinking machines and let's say something else, then I'd actually multiplied with this is a generic what I should say general fully connected linear transformation layer, where we actually multiply with the weight and then add bias, do a ReLU activation on top of it. Again, multiply the weights and then add the bias. So this is the entire the normal linear transformations and the normal ReLU activation that we are actually doing. But there is one small thing which is added upon this fully connected layer, is nothing but all these operations are done at a row level. So the positions of the values are being treated identical, and they have been treated separately. So when they are learning through the entire matrix, apart from they learning the what I should say, apart from the learning the entire complexity of the data, or like understanding the complexity of the data, they're also inbuilt learning the position wise features of that particular position, x1 being at a position 0, let's say. So the position 0 related aspects are also being learned, though we are not explicitly giving in this scenario, that zero aspects are explicitly learned in this position wise feed forward neural network. So post this position wise feed forward network, there is so again, I hope I'm clear till this point.
Can I ask a question, or because of the time constraint, should I take it at the last?
So can we actually extend the session, because I'm sorry, it was a little delayed from my end as well. Anuj,
I'm sorry, Mahati.
yeah, can we little extend the session?
Oh, yeah, absolutely, absolutely. Whatever is comfortable for the group.
Okay, sure.
Mehdi, then in that case, I think I can ask the question.
Yeah,
On the next slide, please.
uh-huh.
Yeah. So here, what I feel is that what I understood till now is X is, suppose the thinking was the word, and at the end of the multi-head, we have a vector, a combination of vector of all the attention. Suppose 8 attentions were there. So all those 8 attentions were multiplied by the weight, and that is the output of one word.
Yes.
Now, when here X is there, so suppose a statement is there, and that statement has 5 words. So every word has a attention after the multi-head. Every word has a matrix where all the attention heads output is there already. So this X is, and so this X is a flattened version of all the 5 words.
No. This is X maintains that position still. So it is directly, yeah, it is a normalized version, I should say, but it just maintains that still this is not flattened yet.
Okay, so it is still in the 2-dimensional thing, because every word is having output of the multi-head attention. So,
Yes.
and its position, relative position.
Yes, absolutely.
And here the max function is applied. That means we are not considering any negative values here.
Yeah. Yes.
What is the possibility of going negative? Because embeddings, what I understand, cannot be negative, if I'm correct.
Not necessarily. So if you can see even in the positional embeddings in the first row, so when you are actually giving sine and cos values as well. So there can be actually negative things as well, many scenarios.
So because of the positional embeddings, the things can go negative. Even the weights can also be negative. Depends on how they are initialized.
Yeah. Yes,
Okay.
absolutely.
Why we are discarding here the negative values?
So I didn't really think about that particular question, but then relu active. I'll
Yes, relu activation. Relu activation discard all the negatives.
yes,
Like,
random activation would actually, but then you're again multiplying with the weight. So it's not that you completely discarded, but I feel, according to at least what I've understood, it's more like the non-linear transformation is usually used to increase the complexity and make the system learn more. Na? So that is the only path which I actually thought of.
okay, so it's the same reason that why we discard, or the same reason why we use the relu as
For
more
the
than zero.
Yes, absolutely. It is the
Okay.
same reason why we actually use it in the neural network scenario as well. That
Uh-huh.
to have that non-linearity in place, such that it would actually learn little in depth.
Yeah, basically it is relu only.
Yeah, L only. Yes, the non-linear
Yes.
aspect. Yeah, yes,
Yeah.
yes,
Okay, thank you.
yeah. Sure. So getting from the feed forward network, getting into the small like sub layer add and norm. So they are actually two parts to it. If you actually see add and norm, what is add is nothing but a residual layer, wherein this particular sub layer would actually do nothing but add the output to the input, like sorry, so this sub layer is nothing but, let's say if it is a feed forward network or a multi-head attention network, so whatever be the output from the multi-head attention or the feed forward network, that output is again being added with my input which has been given. So in this scenario, let's say the output of multi-head attention is being added with the feed forward network. Here the output of input embeddings is added with multi-head attention, so on and so forth. Now the reason why we are actually doing it is for the two reasons. The first being, obviously, there is some learnings that we do it in the sub layer. In the multi-head attention or in the feed forward networks, we actually do a learning of from the input embeddings. Now that has to reflect back to the embeddings. That is one being the reason to add. The second being to reduce the vanishing gradient. So there is a high probability that being this big networks, it has always been the case that your weights, because of the weights, the values would actually get into zeros. Now to overcome that particular feature, we always keep adding the output of just the sublayer, such that a set of values which might actually get into zeros to a set of fresh new values would give me still that that probability of vanishing gradients to reduce to a certain extent. That being one of the major reason why we actually do this residual addition in the entire networks. And this particular add is with is after every I should say every sublayer. Let that be attentions, feed forward, even between the encoder to encoder, decoder to decoder. After everything, we would actually do this, these two aspects. And then the next being the layer normalization. Layer normalization is nothing but you would normalize the entire data to a certain distribution such that it is easy for the next layer to converge. So if the inputs are relatively normalized, it is easy for a sublayer to converge fast. So that is the reason why you would actually normalize the input and then send it to the next sublayer. This is why we would actually use this add and norm feature. So, based on what we have seen till now, at least, we have actually completed till this particular part wherein we actually went into depth of encoders, decoders, and each layers of encoders and decoders. Now, the only aspect that would actually remain from the architecture is this linear and this softmax layer. Now, what is a linear layer? Now, the output of the, so here I just want to mention about the dimensions in this scenario. The dimensions has been maintained to be 512 throughout the architecture. Throughout the architecture, what I meant over here is the input dimensions is 512. The positional encoding is 512. The output of multi-head attention is 512. So throughout the architecture, this 512 dimension is maintained. The reason behind one of the reason behind maintaining this the dimension is also that because of this residual layer. the residual layer has to add upon the vectors every time. So just to make sure that this addition is actually proper, the dimension throughout all sublayers is maintained at 5 level. So to answer your question, I guess, Neeraja, right? That like in this scenario, these are all the input vectors with the 512 dimension. What I should say, yeah, 512 dimensions of each vector. We would actually maintain that particular dimension throughout.
Okay, got it. And if we have less number of tokens, we just put them 0 or something, and then
Yes,
mark it that these are the real tokens and these are not the real tokens.
pad them. Yes, we'll do that.
Yes.
Yes, we'll do that.
Okay.
Yeah. So now the output of the decoder being, let's say, 512 tokens, 512 dimension. But then what we need ultimately is not 512 dimension embedding, but what we need ultimately is a word. If you can actually see aap kaise ho, we need that aap or kaise or ho. Now, how will I actually get aap? That is from the vocabulary. So I need the output of vocabulary size, not the dimension size. So the main aim of this particular linear layer is nothing but to convert the dimension or the output from the decoder into vocabulary size, such that this particular transformation would help softmax to predict the next word easily. That is the main aim of linear layer to be present here. And what is the aim of softmax? Softmax is nothing but, as we have just discussed, it would only assign it from 0 to 1. Like, softmax would assign all the values between 0 to 1. So whatever be the linear layer would output, it would only, assign it from 0 to 1. Like, all the numbers have been, what I should say, normalized between 0 to 1, such that it would predict the highly probable next word as output. So that is how the app has been app kaise ho mein, like every word has been predicted is what is the highly probable next word. So that is the main aim of softmax over here, that the probability distribution has been calculated from the vocab size vector. And also, obviously, the training feedback is taken from the softmax only. So if it predicts correct, it's fine. If it is predicting wrong also, correct or wrong, the loss is actually being calculated also from the softmax output. This being the ultimate end-to-end architecture, and this is one of the I should say famous illustration from J. Almer, that given an input sentence, let's say, I guess it is in French or German, I'm not very sure. So the encoders would encode it into key and value vectors. Now given each each token, like I am I give each token, then the decoder start generating my output as I'm a student type. That being the entire architecture. So hope I'm actually clear at least till this point. Now getting into sorry.
Yes, it is clear.
Yeah, thank you. So now getting into why are we actually picking self-attention? So so these are the intrinsic details of this particular paper as well, from the paper completely, that why is self-attention being used. There are three reasons why the self-attention is being picked up. The first being the computational complexity of the problem. The second being the amount of parallelization that we can do. How much can we actually parallelize? The third being how much long range dependencies can be captured. Now, as we have actually just seen, that in this scenario of long range dependencies, in this equation, a maximum path length, it is O of 1. So we are considering the entire data altogether, and then we could able to capture the data of what I should say, the entire long range dependencies, which is O of 1. That is from the self attention as in a whole. So there is a restricted self-attention as well. Like if I'm actually restricting my self-attention to a certain context, then the values would actually differ, like O of n by r, based on the context length. But then the architecture would actually suggest the entire long range dependencies. The second thing being the amount of computation that can be parallelized. So it is the number of sequential operations that you can do, as we have actually seen, since we are calculating one word, I mean, everything is actually going in parallel. So we can parallelize the entire matrix manipulations at a go. So there is no need of something has to happen, then has to happen, something of that sort. So because we are actually doing entire operations at one go, this is highly parallel, can be parallelized a lot. And as Neeraja, you've just mentioned correctly, that, the complexity per layer, the number of, manipulations that actually happen is more dependent on the number of words in the matrix, like, of n square. So n has been given more importance, unlike the previous architectures where the dimension has actually been given more importance, and the matrix manipulation would actually been done on the dimensions, whatever be the dimensions. But in this scenario, it has actually been the calculated on the number of tokens. So the complexity per layer is relatively high, frankly, when you have a very big number. But then because we can parallelize it so easily, you can actually, the amount of time it takes to converge is relatively less. This is why we actually have, they have actually choose self-attention on top of the previous layers, like recurrent or convolutional layers. Training, they have actually used two set of data sets, English to German and English to French data sets with a certain set of, sentence space. And they have actually batched with 25,000 source tokens and 25,000 target tokens for their batching and then running. Relatively, the English to, what I should say, German data set is higher. No, English to French data set was higher. Sorry about that. Training. So they have actually done one mission training with 8 NVIDIA P100s, and then took around 12 hours to converge for a small models, and 3.5 days to converge for a relatively big model. We'd actually see what is a small and what is a big model. And optimizer, they have used the normal Adam optimizer. And the learning rate, one of the small interesting aspect that they've done is usually in this learning rate, initially what they've mentioned is the learning rate would actually increase in a, linearly till a particular point, which they call the warm-up steps, and after that it would actually decrease. So what is the intuitive idea behind that is, if I have to converge to a global optimum, so initially I can go little faster while we are actually training till a certain point, and post that I have to go little slow. So that is the idea that they have also picked up, that initially the learning rate will go drastically fast, and then they would actually reduce the learning rate. Regularization, they have used the residual dropout layers in between the sub layers and in between the embedding layers. And they've used the label smoothing, which is nothing but you would actually pick up a particular epsilon from the highly probable word and give it to the distribute with the others, and such that the model will be more unsure. But then accuracies were also increased using the label smoothing technique as well. The results, what they've noticed is transformer, even the base model that they've mentioned, which took 12 hours, and even the big model, both of them were actually could able to perform better than all its previous models, that being one. But the training cost was relatively low for them, compared to because they could parallelize it more faster. The training volume is relatively less, as you could notice also. Much of the what I should say, much of the comparison was also with the convolution neural networks than the RNNs. So because they have already considered the baseline to be parallel systems as well. It's not that they're comparing only with sequential models. So that is so even with the parallel networks, the training cost was less and the accuracies were higher. And on top of it, like they could generalize even better. Like I'll come to that particular point. But over here, what they have actually seen is, given the base model, they have done model variations, almost like a hyperparameter tuning, as in they have reduced the heads to one and have seen how the accuracies have fallen down drastically, and they've increased to 32. And then also they have noticed that even multiple heads are actually causing the decrease in the accuracy. So that is one thing. Obviously, the dimensions, if you keep on increasing, the accuracies would actually increase. That is another part that they've actually noticed. And dropout also helped a lot. That is also another observation they actually had. The D part, the dropouts helped a lot. And the other experiment that they have done is, instead of the positional encodings that they have suggested, like the sine and cosine, they have also kept a learned positional layer. So learned position layer is throughout the process, the position layers would also get learned while training. So what they have noticed is, either the sine cos or the positional with the learned layer, both of them are actually doing pretty equal. Like, they're comparable. So that was their conclusion. And then obviously with a higher dimensions and a higher dropout, they could able to achieve better results with a big model. And as I just mentioned, like, apart from just getting the accuracies better, getting the accuracies better for that particular task, the transformer could able to even generalize better. So what they've actually done is, they have trained this particular model on the machine translation task with a very small amount of parsing related information. They have actually seen if the model can actually parse the English sentences well. So what they have noticed is, it could able to do the English sentence parsing as well better, apart from the machine translation task as well. Now, conclusion. Now, this is the conclusion. Future curves at that particular point of time, whatever been written in the paper, because it is quite different from what we are actually having right now. But the conclusion at that particular point is, this was the first model, obviously, yes, which have entirely took out the recurrent neural networks or the convolution neural networks in that place, and then only use the multi-head attention, and have actually could able to get the amazing results. Which, I mean, also they have noticed that this is significantly faster and performs better and could able to generalize better than the previous models that they have actually done. Again, future works at that particular point of time is, apart from like using transformers, apart from this machine translation task, can they actually use it for what they can say, the other set of points? That is one more thing. And also, using transformers for, apart from the text, can they actually use it for other modalities, images, text, speech, sorry, images, videos, speech, and so on and so forth. So that was some of the future works that they have actually mentioned. So if I've just scrolled through to this code a bit. I hope I have time, or
Yeah, Mati, I mean,
yeah.
absolutely, you have all the time.
Sure. Sure. So, if we just get into a little bits and pieces of the codes, you can actually see that. So this is for weight initialization. You could see that, in the feed-forward network, you would actually have the same thing. Feed-forward network was 2 linear transformations and 1 non-linear activation. So the same thing, 2 linear transformations and 1 non-linear activation. The typical neural network architecture, you have a layer, ReLU, dropout, and a layer. Now, in the multi-head attention, as we have actually seen, they are a set of linear transformations on top of your input data. That is the first thing that would actually do. And post that, there is an initialization of the output layer as well, the linear transformation for the output layer as well, which is nothing but you would concatenate all of them and then add upon, right? So that is also initialized to be a linear layer. So now what it does is nothing but this um, scale dot product attention, wherein you would actually multiply your query with the key. Yeah, here. Multiply the query with the key, and then do a softmax on top of it, drop out, and then multiply your this particular vector with the value vector. Do the variations for it to for it to use it for the what I should say, the output layer. And output layer you would actually linearly transform, and then you would get that ultimate z vector. Now from the encoder layer is nothing but like, you know, you would actually have uh, multi-head attention, then the layer add and norm, then the feed forward network and the add and norm. So the same thing would actually happen here. You would actually have a multi-head attention, feed forward network, the layer normalization, and ultimately you would actually add upon. So the first set is for the attention related task, and the second set is for the feed forward network related task, wherein ultimately you would add. So in this scenario, what they're doing is they're normalizing before, and then they're actually doing the entire aspect. So either ways, what the ultimate idea of normalization is, before you get into a sublayer, it has to be normalized such that it will converge, the sublayer would converge fast. So the decoder layer is again the same thing. Apart from that, you would actually have something called as a mask multi-head attention. Over here, it is just a multi-head attention, but the input has actually been deferred. So the only difference, there is no architectural wise difference, but the input has usually been deferred in the mask multi-head attention. You would not give the entire input at once. You would give single tokens once. That is the only difference. But apart from that, you would actually have an attention layer in the feed forward layer. On top of the attention layer. This is the encoder layer, which is nothing but you will have a set of n layers stacked upon each one layer, and each would be actually called for an encoder layer. Decoder the same, and the transformer being the aggregation of all on top of the embeddings. So you have an embedding, a learned embeddings layer, as we have just actually mentioned. This is for the target embedding layers. Now, if you have input, like, you know, if the has inputs is true, then you would actually even assign it for the input embeddings, the target embeddings, then call the encoders and the decoders. This is for the positional embeddings, all the math that we have actually seen, calculating the cosine and like, you know, what I should say, concatenating with the sine and cosine values. That is actually used for the positional embeddings test. And yeah, this is all the matrix manipulations before we give into the encode or the decoder layers. So we'd actually like, you know, get the positional embeddings, get the vocab embeddings, and then add upon and then give it to the encoder layer. The same thing which we actually do for the decoder as well. So at a high level, this is what has actually been done for a what I should say. Yeah, this is ultimately the linear layer, wherein this decoder output is transformed into the vocab size output. So that has actually been done using a linear layer. So that is the whole and soul of like, you know, the entire architecture. So yeah, thank you. And then in case you want me to or like, you know, contact for some reason, you can actually use that as WhatsApp number, and the LinkedIn, we can connect in LinkedIn as well. Thank you very much.
Thank you, Mati. So in one of the slides, I saw something like self-attention and self-attention restricted. What does that mean?
Okay, it's nothing but self-attention, frankly, is nothing but if I'm having a set of text, like usually a sentence. Now, if I'm actually calculating the attention for my, what I should say, for on that particular sentence only, that is nothing but the self-attention, which we have seen as well. So the thinking missions, Meena, we have
Right.
actually seen we are calculating the self-attention only. In the thinking missions only, we are calculating how each are actually correlated. But there is another aspect as well, that the attention is also calculated from one sentence to another sentence,
Okay.
which is not self-attention in this scenario. So I have one sentence and I have, or one input text to another input text. This calculation is not self-attention. So what is self-attention restricted in this scenario is nothing but, rather than me using the entire text that I'm actually having, I would restrict it to a certain length. And then I actually calculate. So let's say I have 1,000 tokens or 2,000 tokens. I'd restrict it to 512, or usually it's 2048 or something of that sort, and then I actually calculate.
So this is to calculate between the like strength of attention that's required between two paragraphs.
No, no, no. So self-attention, as I mentioned, is the attention with itself. Yeah. So in that, when you're calculating attention with itself, I would rather actually prefer to calculate to restrict the length to a certain extent. That is restriction. So if I'm having 1,000 tokens in my sentence, I would restrict it to 512.
Got it. Understood.
Yeah.
Okay.
Yeah, that's the only difference.
Folks, any other questions for Mahati? Okay, let's take a minute and thank her. I know, right? Saturday morning, it is not at all easy, and I'm extremely sorry. I am under extreme weather, so my sound might sound very robotic, but I'm an actual human. Uh,
Thank
Yeah,
you.
thank you so much, Mahati, for this detailed session. I am sure the entire group will be greatly benefited. And folks, we will love to continue with other set of papers, and not just from a technical point of view, but also from a product and a business point of view, right? And that's a holistic picture I will love to have for this group. So uh, please feel free to nominate yourself or your peers or anybody else that you think can add to this group. We will love to learn collectively and grow.
Sure, definitely.